Um, yeah, thanks everyone for being here. Today I'll be talking about using a SAM proxy model for optimization of hybrid solar gas power generation. This work is a combination of efforts from myself and a recently graduated student, Charles Kang, as well as my advisors, Adam Brandt and Lou Drolofsky. So just some quick motivation to this work, to these hybrid systems. Hybridizing solar thermal and natural gas power, as I'm sure a lot of you know, brings about the opportunity to attempt to exploit the advantages of both of the systems while mitigating some of the disadvantages. So we can look to use the low carbon resource of solar thermal while mitigating some of the issues with intermittency that come along with it. So in this work, we're going to look to allow flexible operations of each system and explore whether that has the potential to increase the overall system efficiency and possibly economic performance as well. So just a quick outline of this talk. I'm going to give an overview of the hybrid system that I'm going to be discussing and show what the configuration looks like. Then I'm going to talk through a SAM proxy model, explain what the model is, why we need it, how it works, and then I'll do a comparison of proxy models based on the SAM physical and empirical physical trial models. And then I'm going to go through some preliminary results. So a quick overview of the hybrid systems. There are three main system components, as you might imagine. There's the gas turbine, there's the solar thermal system, and there's the power block. And I'll detail them in a little bit moving forward. But what's important here is the integration has been designed inside our code in a modular fashion so that we can take different types of solar thermal facilities or different types of gas turbines and easily put them into our existing model. So just a quick overview of the way that this system works for us. We have a gas turbine that's coming in and generating some electricity, and some flue gas is exiting that turbine and entering into the power block. From a solar thermal field, where you also have a heat transfer fluid, we're going to use a concentrating parabolic trough with a thermal VP1 as the heat transfer fluid in this example. And its heat transfer fluid is also going to enter the power block. Both the flue gas and the heat transfer fluid transfer their heat into a water stream inside the heat exchange and then create some electricity in the steam turbine, and the flue gas will exit the facility. So the power block here consists of both the heat exchange system and the steam turbine, but we're going to be putting a lot of emphasis on the heat exchange in the coming slides. So just some details on the modules. I mentioned that it's a concentrating parabolic trough with thermal VP1. All the facilities that we're going to be talking about here are 10,000 square meter facilities, and that's just as an example problem. We're going to be exploring multiple different types of facility designs in the future, and this is all based on data extrapolated from SAM. The gas turbine model is based on a paper by Kim in 2004, which gives functions for natural gas part loading, and this allows us to figure out what the fuel use of the gas turbine is at different fractional loads and what the outlet temperatures and flue gas flow rates and so on are. Okay, so here are a couple demonstration configurations of what this heat exchange looks like, and this is what we're ultimately attempting to design in this system. So on the top, the red arrow is the flue gas that's going to be entering the gas side heat exchange, and it's going to come in from the gas turbine, run across a series of different heat exchangers that can be different sizes, different types, and in different arrangements. So this example system just has 3, but a real system would have possibly many, many more, and all sorts of different combinations, and those can be economizers, evaporators, superheaters, or reheaters. And after the flue gas passes through the heat exchangers, it goes out to the atmosphere. Similarly, on the solar thermal heat exchange side, there are a series of solar thermal heat exchangers, which are independent of the gas heat exchangers, and the heat transfer fluid is going to flow through each one of those as well before it exits and, of course, returns back to the solar field to get heated back up. Then we have our water stream. The water is going to be coming from the condenser of the steam turbine, splitting in some way, and we'll talk about that in a second, and then going through both sets of heat exchange where it picks up heat and then run to the steam turbine and produce electricity. Okay, so these are just some example temperatures and mass flow rates that you might see in a system. Notice that the water comes in at the same temperature for both of these systems, but exits at slightly different steam conditions, and we'll have to mix that steam on the back end. The temperature of the solar thermal system in this case is going from 400 to 100 degrees Celsius and has a mass flow rate of 15 kilograms per second. But something that we might look at doing is exploring an alternate water flow path configuration. And if we do that, and say we look at keeping the same heat exchanger layout, but bypass the economizer and the superheater, and only use the evaporator in the solar thermal section, the temperature difference, you'll notice, in the water stream in the solar thermal side goes down a lot because it's essentially only handling the approach temperature inside the evaporator. And so when this temperature goes down substantially, the mass flow rate of the water goes up, but also importantly, the temperature differential on the solar heat exchange side that's required goes down substantially. And when this goes down, the mass flow rate goes up. So this kind of gives us a motivation. What we really need to solve this model effectively is a mass flow rate as a function of the inlet and outlet temperature of the heat transfer fluid. So I should mention that each one of these configurations, the way that we solve it, it's a series of nonlinear equations. For each heat exchanger, there's an energy equation, there's an effectiveness equation, and there are continuity equations for the mass and temperatures on both sides. So this can get fairly large. If the number of heat exchangers is large, we can get some 150, 200 equations, or it can be a lot smaller, depending on what the system configuration looks like. Okay, returning to this idea that what we need here is a functional form of temperature to get mass flow rates. This is what motivates our need for a proxy model. So in order to be able to apply optimization to these types of systems and to look at how everything should be designed and operated, we're going to need, based on our estimates, somewhere between 10 and 100 million function evaluations. So these need to go quite quickly. And what's important is that we only need to be able to analyze 1 hour at a time. And the way that SAM is set up to work, it's intended to analyze the entire year. So we're going to try to make a proxy model that can handle this on an hourly basis. And we also want it to be a smooth functional form, and that's so that we can have clean derivative estimation inside of our system solution. Okay, so the proxy model that we came up with has a simple functional form. It's the mass flow rate of the heat transfer fluid is equal to C0 minus C1 times the outlet temperature of the solar field divided by the temperature difference between the outlet and inlet side of the solar field. Now what's important here is that this is for 1 hour of 1 day of the year. So you'd have to repeat this model for every independent hour. That's why you don't see terms like irradiation or ambient temperature or wind speed, because these are all built into these C0 and C1 coefficients. And the way that we're going to solve for these is by taking a set of sample points out of SAM. We're going to explore different outlet and inlet temperatures at the same design, run SAM across all 8760 hours of the year, and then for specific hours, do a nonlinear least squares fit, and then test it on a variety of points. So here's our proxy model performance. These are composite results for multiple hours. This is a day in August. The day does have some cloud cover moving across it, so we made sure we could cover that. This is using Sam's empirical model, not the physical model. I'll talk about that in a second. The training set, as I mentioned, was based on a set of fixed interval points, so it's across a grid of feasible points, feasible meaning the outlet temperature exceeds the inlet temperature. And we created a random set of test points at different temperatures, and these are the plot of the test temperatures, where on the x-axis is the mass flow rate that Sam predicted, and on the y-axis is the flow rate that our model predicted. And what you can see is that there's very good agreement. Everything sits nicely on that 45-degree line, and our RMSE and mean absolute error are both quite low for that range. So we have a good working model. And here's a little bit of physical interpretation, just to see that it makes sense. So this is then applying that proxy model that we've just created over a surface. You can see that the region where the inlet solar field temperature, that's on the bottom axis, is less than the exiting, or exceeds the exiting temperature, which is on the y-axis. It's infeasible. And we put an extra constraint there saying that the temperature actually has to exceed 30 degrees higher than the inlet temperature. And the behavior is what you would expect. As that temperature differential gets low, the mass flow rate gets a lot higher. So if we compare this result of the empirical model, which is on the left now, to the results, if we repeat the same procedure, we had to put the data filtering method in, but if we repeat the same procedure on the physical model, we get a slightly different set of results. And visually, they look roughly approximate. There's some disagreement. But if we take these and subtract each other, in general, the physical model produces higher mass flow rates than does the empirical model. If we take the difference of those and overlay them, we can take a look at the model deviation. That's this plot here. So this is a note that this is a different axis than what the previous slide was. So this is the difference between the two models, and that difference can get all the way up to 25%, even though for the majority of the space it's quite low, in the 2 to 5% range. And my personal hypothesis for this deviation is that the empirical model, which is based on a real facility, probably didn't explore cases where the entering solar field temperature was very high and the exiting solar field temperature was also very high, because it was built for a traditional type of concentrating solar thermal facility, in which case you're not going to run in that regime. But if anyone here has any other insight or explanation as to what might cause this deviation between the models, I'd be really interested to hear that in your feedback. But going forward, we've been using the empirical model simply because the empirical model is a more conservative metric between the two. It's got lower mass flow rates, and so just to be conservative, we've chosen that model. So here are some preliminary results. So taking that proxy model that we've now built and putting that back into our system, we're going to look at different hours of the day. And these hours are not linked up together. So hour 12 does not move into hour 13, for example. They're completely independent of each other. But it just shows you how the performance changes over the day. On the y-axis, you can see the electricity output, and the dashed blue line shows what a gas turbine with heat exchangers and its own steam system, but without any solar thermal influence, what that system would perform at. And then we can look at what the hybrid systems would perform. The purple dot is the lower system configuration that you can see down on the right-hand side. And in that system, the water stream runs through all 3 solar thermal heat exchangers in this example. And at the green dot above, we use a different water flow path where instead of running through all 3 heat exchangers, we only run through 2 of those. And what you can see is that the electrical output is different for those 2 systems, as we might expect. So that leads us to think that there might be an optimal configuration that we can go after. Another kind of important aspect is this kind of shouldering effect that we see over on the left-hand side. There's 1 hour of the day. It's only a single hour here, but there is an hour of the day where one configuration can produce electricity and the other configuration cannot. And the reason it can't is simply you can't get heat transfer fluid hot enough in that particular hour to run through a superheating section. So it's an infeasible solution. So that's important because by exploring alternate configurations at different hours of the day, we might be able to extend the shoulders of the day and produce more electricity over the course of the day, as well as in a given hour produce more electricity. Okay, so wrapping up with some conclusions, we've produced and demonstrated a model that can evaluate different hybrid solar gas operational configurations and possibly explore different designs. It's based on a proxy model for SAM, which we've demonstrated has fast system evaluations while maintaining accuracy. Different hybrid system configurations do appear to produce different electricity outputs. And in our future coming work, we're going to be exploring both optimal design and coupled optimal design and optimal operations of the facility using the modeling approach that we've outlined. With that, I'll wrap up, and I'll be happy to take any questions you might have.
Great. Thank you very much, Phil. If anyone has any questions, if you could please type them into the chat box now.
Hi, Phil. My name is Ty Nices at NREL. I've done a little bit of hybrid modeling a few years ago, and I'm curious. A few slides from the end, you showed the gas turbine output without solar contribution as a constant output. I'm sure you guys know that typically that value fluctuates as the ambient temperature changes, with high ambient temperatures resulting in a decreased output. And a lot of the benefit people claim that hybridization will allow is for that solar contribution to be highest when the gas turbine output is lowest. I'm curious if that's something you plan on looking at a little later as your optimization process goes on.
Yeah, that's a good idea. The question is exactly what we're going to be looking at on the operational side for hours of the year and how deep we're going to be exploring that. It's something I'd really love to get into. Our gas turbine model as it's built now can't handle that, but it's something that one of the other students in our group is working on enhancing that model. And so we'll hopefully be able to incorporate that in future work. But for right now, it's, as you noticed, it's flat and doesn't have any effect. But that would be a really interesting thing to explore, and we'll take a look at it.
Yeah, I think this is really good work. The research space here is really wide open, and there are a lot of things to look at as you guys are starting to figure out, I think. So yeah, all of your results I think will be pretty useful in general. I'd also comment on your question about the difference between the empirical and physical trough models. Like you said, the empirical model is based on measured results, so you can expect those to be probably most accurate for whatever they were measured for, correct? So I think it was from a CEGS plant that the trough performance was, those curves were generated from. The physical trough, I don't know what case you're using, but obviously it's more configurable. You can look at more alterations, different designs. So the idea of the physical model is it's better at helping you understand differences in design changes. So if you're looking at different emissivity coatings or different diameters, different configurations, the physical model helps you do that. So it's probably not really fair to compare both of those models unless you know that your physical model is representing CEGS, which I don't think we tried to do in any cases that NL produces. So I think using empirical models, one-to-one comparison between that and the physical model probably isn't super useful unless you put a lot of time into making sure that physical model is representing that SIGS model.
Right, and that's what we anticipated. We just thought it would be interesting to compare the two. What are your just to see how the performance worked? So in general, your thoughts would be that it was a little unclear to me how the physical model might have been verified for actual field tests. Can you comment at all on the verification process that's gone on? You know, how accurate can we expect that physical model to be?
Yeah, I mean that's a good question, and as you can imagine, companies are pretty close with their data. We haven't, I don't think, published any validation on it. We have worked privately with various entities on their trough, and the performance of that model is fairly accurate if you know the dimensions and the parameters that you're putting in, which is always a bit questionable because those are also usually proprietary. Steady state, it does well. Transient 10-15 minute performance is a little harder to hit because of other things happening in the plant. But in general, it's accurate enough, I think, especially for this type of research. But that being said, if you guys are more focused on the power cycle side and you just need something that's representative of the trough behavior, then I think your approach is good.
Great, thanks a lot. Really appreciate that.
And Phil, we have one more question here before you wrap up. What would you say would be the biggest improvement to SAM to enable further research in this particular area?
So, from a personal note, having SAM be able to look at different lengths of time in its analysis would be really useful. So if we could get it, and perhaps there's a way to get this to work that I'm just not aware of, but as I see it right now, you're constrained to operate SAM over the duration of a year. So we could just narrow that range to, if you happen to be interested in a particular hour or a particular week, those are analysis that SAM seems to be able to run anyway. So just being able to limit that frame of execution to speed up the evaluation, that would be very useful.